This is the last video in the first lecture series on rotational mechanics, and the topic of today's video is the spinning gems. To answer any of your questions of why is Mr. Meyer wearing that hat in these videos? Well, I'm showing my support for the Syrian family that made this. I went to an exhibit yesterday on the Syrian refugee crisis, and I got this lovely hat. So that's why I'm wearing it. But to the physics, recall that our linear gems from our early days together go something like this, and you can find them on your equation sheet, so there's no need to try and memorize them yourself. And I'm going to try and convince you that for every kinematic gem, there's also an equivalent rotational gem. So I'll derive one of them using this first equation, but using the same process, you should be able to derive the other two. I'm just not going to do it here because I hopefully can convince you that this would work. It's relatively simple. You take your kinematic gem, and you have your two relationships, and technically there's a third one, right? You've got the displacement is equal to, not displacement. The linear displacement is equal to the radius times the angular displacement. And you know these relationships, so you just plug it on in for the linear component. So for linear velocity, I would put the radius times angular velocity, and I'm careful to note that this is an initial speed, so it's an initial angular velocity. And if I plug in for acceleration as well, then I notice that every single term has an r in it, so I can divide everything by r, which will cancel all of them out, so I'm left with that expression. If I did that for the next two equations, then I would get something like this. You might want to pause the video here so that you can get these 6 equations down. So this expression corresponds with that one, and so on. So these are our kinematic gems for spinning objects, for rotating objects. Now let's put that to practice. A bike wheel with a radius of 0.3 meters starts from rest and then is accelerated at a rate of 4.5 radians per second. Oh, that should be squared. For 11 seconds. What's the final angular velocity? So I look at my problem and I try and figure out what information I know. Well, it starts from rest. This object is, keep in mind, not moving forward or backward. It's just sort of hanging and you're spinning it faster and faster. So my initial angular velocity is 0. My acceleration is 4.5 radians per second squared, and the time that I'm accelerating this bike wheel is 11 seconds. So I pick out the appropriate expression. I'll just go from top to bottom and see if I can find it. This one has the angular velocity. That's what I'm trying to find. Has initial angular velocity. I have that. I have this. I have time. So I could use it. I plug in, and I get an answer. The answer would be in radians per second, which makes sense for angular velocity. Another question we could ask is, well, what's the final linear velocity of the wheel? And if I know the angular velocity and I know the radius, well, I have a relationship that relates these two and the linear velocity. Plug and chug, and I get an answer, and that's in meters per second. Remember, because radians technically is unitless, so I just have meters per second. And perhaps maybe the most interesting of them all is what's the angular displacement. So if the bike is accelerated for 11 seconds at that rate, how many radians will be swept through, or how many revolutions will this bike make? So let's say it starts at 0, the angular displacement is 0, and the angular speed is 0 to begin with. So I pick out this kinematic gem, the second one. I can cancel these two terms out because they're 0. and I'm left with 1/2 times angular acceleration times time squared, both of which I have, so I get 272 radians. It's hard for us to make sense of what that is, so I divided by 2 pi in order to get something in revolutions. So for the 11 seconds that this wheel is accelerated, it covers 43.3 revolutions. That's all for the spinning gems. Hope that made sense, and I will see you guys soon.